says we're live on
Twitch?
Streamlabs. I'm going to check Twitch now.
Yeah, we're loading Twitch. Yeah, we're live.
I've got it live on Twitch. Okay, so my computer, my other laptop, is doing great because there's something. Okay, all right. So hello and welcome to Programming Bitcoin, where we will program Bitcoin after we figure out how to stream live on Twitch, which apparently
Which we just did.
Yeah, we did. Apologies for anybody tuning in or watching this. Well, I don't know if anybody's going to tune in, but apologies to anybody that wanted to tune in that catches this later. And I need to just catch up. We had some technical difficulties. My other laptop is on the fritz, so that's always lovely to experience when technology doesn't work or do the thing that you want it to do. But we're going to add some. This is Pleblira up there on the top there. You can find him on Twitter at Pleblira. And then myself,
What's up?
Go by a different handle.
You are not the chronicler.
I'm not the chronicler. Nope.
Even though that's kind of a cool handle to have on Twitter.
Yeah, I might. Maybe I'll change it.
Yeah.
So we'll see. We'll see if it's available first. But yeah, that's it's the name of a project that I want to work on and do meaningful things with. So maybe I will. One day I'll change it. But
okay. So that wasn't. I know Keith will pick like random names for us. That wasn't the case.
No, that was not. The chronicler is something that I came up with.
Okay. You don't need to, give any more details.
Yeah,
wait for the project to come out.
It's we'll wait for the project to come out. We'll see how it goes. But let's just see if the chronicler is it's available.
True.
That's it.
You might want to.
Locked it in.
You might want to snag it now.
I locked it in.
You locked it in just now. Okay.
Yeah. Did I spell it right? CHRONICLR. Yep. All right. That's my new Twitter name. Cool. So, for anybody tuning into the live stream now that might not know,
the chronicler is not available anymore. That handle.
I'm now the chronicler.
You're never gonna have it.
And you cannot be. But let's chronicler at the chronicler Twitter. I'll just add it out there for anybody coming along. And watching these videos later that might not be listening, they can at least see the chat handle, which my MacBook wanted to put period because it did double space, but that's fine. All right, we'll call that good. This is Programming Bitcoin in Rust. I should put a title up there too. I'm sorry for anybody watching the stream now and like wondering, like, what are they doing? Oh my gosh, like, why are they setting up the stream now? I was streaming from a different laptop previously, and that laptop is not working anymore. So we are we have lifted and shifted to a completely different laptop, and we just tested the stream, and we're gonna stay live just because we're live, and we'll kind of see what happens. We're using Keet.io to peer-to-peer messaging, and do you want to talk about what we went over last time? Now that we're actually live, like now we actually have a live thing, and we can try this again where we talk about what we did last time.
Yeah, right now we are doing a Twitch stream scene workshop because you're setting up the scene in real time for everybody to see.
Right, yeah.
But that is not what we do in this channel. What we do is called Bitcoin in Rust. We are going over Jimmy Song's Programming Bitcoin, but instead of using Python, we are using Rust. And last week we started going over like the second half of chapter 3, elliptic curve cryptography. and it's like when it starts getting really, really interesting, we are starting to work the parameters for public key cryptography,
Yes,
signing
sir.
and verification, setting the target for when you're building a cryptographic signature, and all those lovely equations on that section. So it's like page 61 through 65 of the book.
Yeah,
And we also did some refactoring.
We did. I've got I don't know how to put a background on that, but I'm just not going to. So we'll call it good. Yeah, we did some refactoring. What were we refactoring? We were refactoring from. We started out using, was it uint, or not uint, U64 as our types for the field elements, and that was not big enough for Bitcoin, and so we had to go to big uints or big wints, as we like to refer to them as.
Yeah, which is something Python doesn't care the size of the numbers. You don't need to specify types in Python, of course. But since we are doing it in Rust, for the beginning exercises in the book, like the first 2 chapters and even the first half of chapter 3, 64-bit numbers, 64-bit integers were fine. But when you get into 256-bit numbers, Python wouldn't have a problem with that, but Rust did, so you had to refactor it.
Yes. Just gonna block somebody that's in our chat trying to solicit us. Yeah, it is, and that has to do with the memory. Like Rust is a compiled language, so it concerns itself with memory. It's a systems language. Python is not, and so it kind of does things. I don't know how Python does it all, but it does things differently than Rust does. That's for sure. Python, you don't have any types that you have to worry about. It's all kind of like a dynamically typed language. So,
I guess the performance between the performance difference between the two languages speaks for itself.
Right. Yeah, and it's you're not guaranteed performance when you're using systems language, but it just is going to tend to be faster just because it doesn't have the overhead of managing of on the fly sort of garbage collecting is what it's called, where you sort of just fill up a bunch of memory and then you dump it all when it's not used, or you hope it's not used. And let's see, where were we at? We're on the end of chapter 3, right?
Mm-hmm.
Public key cryptography. That's
where we were, yeah.
And we're live. Let me. I'm gonna make a note on Nostr for
okay. Let's do that
for what we're doing. Difficulties, and then we'll jump back into talking about what we were refactoring. So the refactor. Let's look at that, and we can look at that holistically without looking at the programming Bitcoin. So let's go over here, source control to our commits. I think we. Oh, you know what didn't change? Are you in the live share here? Did I? Yes.
Yes, I am.
The README we added. We added a README. I need to pull that down. But what we didn't do is I didn't. This is no longer correct.
Where's the README? Is it on the root?
Yeah, it's in the root. So I just did a git pull, so it might take a second for your side to see that.
Okay, yeah, because I'm not seeing it on my side.
No worries. And then this is different code. Bitcoin in Rust is the name of the new channel. That's fine. We'll commit and push that. I don't think we pushed in the last one. That's okay. It probably wouldn't work if I tried to push from that other laptop because that other laptop is broke. Created the README print leading zeros. Oh, this was just something that I saw in the book itself, that it the way it printed out these field elements. I did a similar thing here where you basically tell it how many characters you want. I haven't tested this though, so maybe this won't work. But
like the Z fill thing, right?
yeah, the Z fill thing, to make sure that you're not dropping any leading zeros for when you're printing these things out. All right, here it is. So test pass now. this was because we had a bunch of tests, if you recall, that were failing. And so something that I had to do, again, this was me modifying the display of the field element to kind of see what was going on. Not super relevant. This, so a lot of the refactor that I did was using functions. So the big wint, or the big uint type that we migrated to, like there's a whole heap of functions on that type. Or on that struct, or implemented for that struct, rather. One was this remainder function, which I don't know if you remember, but we used this REM previously, and I can't remember where it was, but we used it before, and it was just a remainder function, but it does basically the same thing as like remainder, or the modulo, the percent sign. I can't remember which one it is, but yeah, that's so we updated that.
Was it the Euclidean remainder or something like that?
Right? Yeah, Euclidean remainder. Man. And then I did a few other things. So some of these were pretty simple. Like the addition one was simple because going from 7 to 12 worked. These broke, however, still after, I can't remember what it was, but it basically, like some of the, never mind. For the field elements, they worked because it's just field elements adding to each other. So like it was very easy to do multiplication and like exponentiation, division, etc. The division was actually difficult. I had to. That's why I updated the way that it was printing out the format here, because I needed to do the division to see what the answer was, and just trusting that our code worked. But now we were just using bigger numbers, right? So that was for the field elements that I got the test passing. The next thing was the point struct, and the implementation, or more specifically the SECP256K1 point. And this had a few changes here. So in this, it was just sort of refactoring this algorithm that we used, that I think we found on Stack Overflow or something like that. But it was basically how to do scalar multiplication by using this shift, this bit shifting.
Bit shifting, yeah.
And the bitwise operator to check like if that bit was a 1 or not. So with that, it had to come. It was a because we were changing coefficient, so this coefficient was being bit shifted. It wanted, as a big uint, it needed to be a mutable reference, meaning it's not the direct value. It's a reference to the value, but it's mutable, meaning it can be changed. And so instead of doing this, where we just sort of like, I'm pretty sure this did a copy underneath or a clone underneath because of because it's a base type, like it's a primitive. So because it's a U64, anything that goes on the stack, which a lot of these primitive types go on the stack, they implement this like copy trait, meaning you don't have to necessarily like clone them or do something special. It just like magically will, oh, you want coef to be coefficient, so it will just copy that sort of thing. But when we migrated to using the big uint or the big wint, because this is allocated in the heap, and it's a pointer to a section of memory, and it's not on the stack itself. Now it didn't, like big wint doesn't have that copy trait, which is again why this is also why I had to like clone the value, because you couldn't Rust doesn't like when you modify things that are going to be referenced later. So because we're referencing this in each iteration of the loop, if we try to modify the coefficient in the loop, it gets weird. Because it would, like, so this if statement was consuming the use of the coefficient as a variable, and that has to do with like the Rust ownership model. And so instead I just cloned it, and this might not be the most like performant or optimized way of handling this. Like there's probably some Rust wizard out there that will watch this and cringe when they see, you know, all these clones in here. But it worked, and it was late, and I was hacking on this at night, and I was like, okay, this finally worked. Another thing,
it's not like you're going to be multiplying, you know, 256-bit integers.
Right, yeah.
Oh, right.
But it's not even it's not the performance thing. It's the memory. So like the amount of memory. So 256 bits of space in RAM, right?
Oh, okay.
So that might matter for like a Raspberry Pi, but even then, Raspberry Pi is like a modern Raspberry Pi has like 8 gigabytes of RAM or something, or 4 gigabytes of RAM. So it's still not that bad. It's just I just know that this could probably be optimized more to be more performant, and I'm not as proficient with Rust and the whole memory stuff like to do that. Right
okay, but
nor did I care, right? Like it was also not like it would require some effort on my part to like figure out what it would be. So I just didn't do it because. And then again using the like I mentioned before, using the functions on the implementation of BigUint. So the bit and so like this the bitwise operator is this bit and function. Couldn't use just a 1 because in Rust this 1 is considered like a assigned integer 32. So I had to use again comparing a BigUint to a BigUint sort of thing. And then again cloning it before we shift it and then reassigning it. And this star is a dereferencing, and that's like saying, hey, we're not changing the reference, we're changing the underlying value that reference is pointing to. And this is it does the same exact thing as the side on the left is previous when we were using U64, and the side on the right is now just refactored with the BigUint.
Nice.
So that was a scalar multiplication part of it. Any questions?
No.
Okay.
Yeah.
The gist of it was just use functions. Use the functions on the class, or not class, but the functions for the struct of BigUint. This was, okay, so I did something, first of all, none of the points that we had here, right, were on the curve, on the Bitcoin curve. So in our old test, we had all these points that we were defining to do equality tests, and we were doing the identity test where you were adding, the same point to each other to get to the infinity point. But like none of these were on the curve, and I didn't want to sit there and figure out like what points were on the curve to plug in here, because it would be like, again, it was just a matter of like time, and we could do that if you want to do that, but that was why I sort of commented out all of these tests here, because I felt like it was for the purposes of what we're doing here.
We will be focusing on the Bitcoin curve.
We're focusing on that. And then in the actual book, it has, we'll zoom in here a little bit on the book. It has sections where it talks about verifying the curve, right? And so that's what I modeled these other tests off of. So it's not verifying a signature. Where was it? Similar to that. Here it is. This so verify the generator, and we can get out of the diff. We'll go to point, and verifying the generator point is on the SCCP 256K1 curve, which I basically copied this section of the book and made it a Rust test, because that's ultimately what it's doing here. Is it's creating a test. So yeah, taking the y to the power of 2, the prime number, modding it by the prime number. We use this prime number again. So this clone, we use this prime number down here. So if we consume it here, then it's not usable down here. It didn't like it when I used it as a reference, so we cloned it again. Again, it's a test, so I'm not worried about performance really for a test, but maybe you are once you have like thousands and thousands of tests. But
like the last time you mention a variable, then you don't have to clone it because you can consume it.
Yeah, and that goes into Rust sort of like scope, like the way that Rust manages its memory is it makes sure that you're not going to be referencing a point in memory that's either not there anymore or has changed somehow without the compiler knowing that it's supposed to change.
Can you say that again?
So when we create this big uint, right, this prime here, this is creating something on the stack that is a pointer to something in the heap, which is like the RAM, right, the memory. And so in like C and C++, which I've never done, but to my understanding, having gone through Rust, the way you would have to sort of manually manage, like, to make sure that that pointer actually has something in the is allocated memory somewhere, right? Because if you use that pointer and it points to a section of memory that's not allocated anymore, or that is changed, you can get undesired side effects and cause issues. And there's some like study about like how like that can cause. There's a lot of security vulnerabilities over the years that have been caused by that sort of thing. And so what Rust does is it forces you at compile time to manage this memory in a way that is safe, where you're not going to reference either memory that's changed without knowing, or and that's where that mute keyword comes in, the mutable keyword, or you're not going to reference memory that's like already been used up, consumed, and has been removed from the heap or whatever.
Nice.
Yeah.
That's great.
So that was the first test, was just making sure this is on the curve, and the next one was just the next one down, where we're verifying the generator point of the Bitcoin curve, which you posted. Was that on Twitter or was that on was that a Nostr post?
On Twitter today.
It was on Twitter, but it's what did you say?
It was like, can you just tell me how many times I should add the generator point to itself to find your public key?
Right. And why did you say that?
Because this is actually the number of times you have to multiply to it. The number of times you have to add the generator point to itself is actually the private key.
Where did you learn that?
It's the equation, the P equals EG, or EG equals P, on page 63 on the book. Like that.
This one right here. This?
Let me see. Yeah, this one. So what this equation is actually a scalar multiplication of the generator point. It's equal to the public key. And the number of times you're multiplying the generator point is the private key. So it's like, it's just a number that I'll multiply the generator point whatever number of times. That's my private key. It's like so ridiculously simple on the surface level, of course.
Simple, yes. Yeah.
It's just a number, you know.
I'm wondering. Yeah, because it would be, or you could also say how many times do you have to add your private. Well, hold on. How many times do you have to add your private key to itself to get to your public key? But that's
How many times you have to add the generator point to itself, or multiply the generator point, basically?
yeah. I'm trying
Yeah.
to remember the. Oh yeah, because the private key is not a point.
No, it's just an integer,
It's just a nut.
really big one.
Yeah. So that's why it's the scalar multiplication of the point, the generator point itself.
Mm-hmm.
Can you? Oh man, I wonder. Okay, say something.
Can you hear me?
Okay, yeah. I didn't with the
Um.
new setup. I wasn't sure if our levels were good.
Oh,
Like
right.
I wasn't sure if you were coming through on the levels. So I think we're good. But
I did. Okay.
see how it goes. Um, but yeah, this was so, and this was interesting. So verifying the generator point has the order of n, um, which to your point makes sense because the generator point is like the first point in this order, or this big group of numbers, or this big group of points that is on that curve, right?
Yes.
And then like the order stops when you hit the infinity point, because you've multiplied, or you've multiplied it by, you've added to itself so many times that you hit the infinity point, which is basically like the 0 point, if that makes sense, of this curve. And so by this math here, verifying the generator point has the order of n, which I guess we should have changed this to n, but
Yeah, you could.
because when we multiply n by g, or yeah, when we multiply n by g, we get to
Infinity.
The infinity. Yeah, so we multiply the generator point by n, we get to the point in infinity, because that defines the whole set.
Mm-hmm.
So just like you were saying, how many times do we have to add the generator point to itself to arrive at the infinity point? It's the size or the order of this whole finite field, which is, like one of the constants of Bitcoin.
Yes.
And that order is, oh man, I'm trying to figure out how that order is defined. Oh, the order is just defined that it's just the number that you hit infinity at using the prime number, because for this finite field element, or this group of finite field elements, every time we're moduloing aspects of it by the prime number that is Bitcoin, like the Bitcoin prime number, which I had defined here.
Is that n?
I think it should be. No, I mean, I think we defined it statically. We must have done that before. No, n is the order. The prime is a different number.
Oh, okay. Like the 2 to the power of 256.
Right. Yeah, and I'm trying to remember. Oh, here it is. Oh, we did define it in these tests. I'm blind.
All right.
Yeah, so again, using the big uint, we had to use functions to, like, 2 to the power of 256 minus 2 to the power of 32 minus 977. And that's like the big prime number that all of the magic internet money. It's okay. It kind of blew my mind when I was thinking about this. Like, it's like just this one number. Like, this one number enables Bitcoin.
Yeah.
Which, once you've been down the rabbit hole, you know sort of what Bitcoin is. It's kind of crazy.
So that's the prime number. How do we differentiate between the prime number and the n, the order n? Now I'm confused.
So the prime number just defines.
The prime number is for the field element.
Right.
And the order is what you generate the adding the points. I mean the order, yeah.
Right.
They're not the same thing. Yeah.
Well, in the primes, what you're moduloing by every time.
Mm,
I don't.
yes.
Yeah. Um.
Yeah, I was kind of bundling them together, but they're not the same thing at all.
And then I looked at this portion of it, the zfill 64 thing, to make sure we have leading zeros. We kind of did this next part where it was basically creating a class where we don't have classes in Rust necessarily. We just have implementations. So this 256 point is, we have that already. So let's oh, excuse me. It is late.
Yeah, we might. Yeah, we're just doing a review today, probably.
Yeah. Another thing is it didn't like.
Okay.
Go ahead.
No, go ahead. I'll bring up something after you finish this.
Oh, I was just gonna say it doesn't like having constants that are not, so like I wanted to define a constant,
Mm-hmm.
and it didn't like when I did that. And I can't remember why. This is another one of the Rust things that I'm gonna need to figure out. I haven't quite mastered. Is that right? I think that's right. Oh yeah.
You're creating the constant for the generator point.
Yeah, I was gonna try to create the content, but it didn't. It didn't like what I was doing. What is going on here? It doesn't like this U32. Mismatched. It says mismatch type expected and got result. Oh, we need to unwrap it. Unwrap. Which is probably not the best thing to do. But yeah, I didn't like when I defined these constants this way. And I just wanted to show you the error that Rust was giving us. Yeah, this. So
what is it saying?
It's because the we could probably define this, but it's because this from string radix has a result type. So result means it either is gonna it's okay or it's not. And so it didn't like that, and so there might be an easier way to sort of define this constant variable by specifying a big uint sort of I don't know, natively maybe. I don't know how to. I don't know. We would have to look through the functions of big uint. At least that's how I would do is look through a functions of big uint to sort of find a way to define a constant. But we can worry about that another day when we're not so tired.
But what I said earlier, that checks out, right? That the private key being just a number, the amount of times the generator point is multiplied to get to the public key.
Yeah, and I think we'll probably go into generating private keys. I mean, I'm almost positive.
And then we can run tests to confirm that.
Yeah. So let's do that. This talks about the signing. We went over this last stream as far as the signing goes and public key cryptography. Mm-hmm. The verification of it. So verifying a signature.
Okay.
This is so this is another test that we could write here to sort of verify the signature. You want to write this test? All right. So let's get down to the bottom there. Yeah, we'll write this test and we'll call it good because it's been a frustrating night of technical difficulties.
You're starting here before the comments.
Yeah.
That's it.
Pound, square bracket.
Yes.
Yeah.
Oh, you didn't. Yeah, you.
So we have to define. So we can define. These are all. Are these all numbers? I guess I'm assuming. Yeah, I think these are all numbers.
Yeah, hex
because they're
numbers.
hashes. So we can define these. We'll just define these as biguants. Unless for some reason that doesn't work. String radix. We'll give it the string, and the radix is going to be 16. And it's going to be just copy.
I'm pasting your Z here for you.
Oh, you got it. Oh, my bad.
No, that's all good.
You don't need the 0x on the front of it.
That's what the string radix is saying.
Yeah, the radix part of it is saying it's a hexadecimal, and then we got to remember that we're gonna unwrap these.
It's whatever base, and then you put 16 to explain that it's hex.
Yeah.
Right.
And then S.
You could do any base there, really.
Yeah. Which is kind of fun to think about. Like, I wonder, now that I know this sort of weird math that is like elliptic curve cryptography and modular arithmetic and all this stuff, it's like I wonder what other like weird mathematical like patterns are in other, like in other bases or even just like other sorts of ways of doing math. Intriguing. You want to do PX? I'll do PY.
Okay. Did you break all those chunks down into lines with a simple command or just one by hand?
Oh no, that was when I hit save.
I had like a formatter or something.
Like that?
Is that like a formatter or something?
Yeah, that's just that's a formatter, and it's in VS Code. I'm sorry, I probably messed with you while you're trying to edit it on yours.
No, no, it didn't, because I had figured out what I was doing wrong. It was an extra parentheses there. PX there without the hex. Base 16. Unwrap it. Interesting choice that he'll add the unwrap method in a new line. Yeah.
Why is this not like this? What's happening here? Oh, it's a field element. Duh. And then PX.
Yeah, same thing for PY, yeah.
Yep. Colon new.
Yeah, PY. Cool. You don't have to define the prime for these field elements.
No, because remember we set that, so whenever you new it up, we calculate the prime and assign it. This is probably another instance where we could define a constant. So we're not like recalculating this constant number every time. So we should definitely do that. We should definitely define that constant just for performance perspective, because you don't want to calculate this big number every time you have to create a new field element. It's gonna cause issues down the line. So.
Oh, okay. So you kind of, what's the word when you're like, I guess that's not the word, but you made the field element class, whatever is the name in Rust.
Yeah.
Just work with this prime for now, since that's all we're going to be using.
Right. Yeah.
Like if you were to use with a different prime, you would have to edit the class again.
Exactly. Yep.
Oh, okay, makes sense.
Yes. So what are we doing next? What's the next one? S inverted. So slope. I'm assuming that's slope. And that's this. Oh, this is the division. This is the
Exponentiation.
Yeah.
You had a.
Pow.
I remember. Yeah, it's just the power function. Nothing.
Oh no.
I had the 3 parameters, right?
Yeah, but this doesn't.
No, you're saying division because the prime -2. Yeah. I remember that.
But the POW for this wants a unsigned 32-bit. So how do we... Oh, man. I'm curious how we did this elsewhere. And I'm not sure that we have.
I don't think so. I don't think we did any.
Oh, wait. Or was it? Yeah, it's mod POW. That's what it was. Sorry. I was wondering. Okay. I was like, POW just takes a U30. Like I knew we had done this before. But yeah, mod POW is the exponent and then the modulus. And the modulus is... The exponent is n, which is the... Is that the prime or the order? This is where we need to have constants. We should just have constants.
I think it's the prime. Because we're just exponentiating field elements.
Yeah, it's the the prime -2 is the how you do that one. You're right. It is the prime. So we need to define that, which we'll grab it here before we... Yeah, see, we're declaring this in every test, so this is just not that great.
Oh, okay. And you're having to do this because it didn't allow you to set up a constant there. Okay.
Right. It's not that it didn't allow us, it's just... I didn't take the time to figure it out.
Mm-hmm.
And then this was the prime.
Okay, cool.
All right, and that should work.
And they're just yellow there because they're not being used, right? Just a soft warning.
Yeah, this is just a soft warning, unused point.
Okay.
So we've got that, and then we calculate the U.
And okay, you add U, I'll add V.
Done deal.
Alright.
So I think he's gonna yell at us in a second, but we'll see.
We have to add the thingy here.
Maybe. Oh yeah, that worked. Need to add this here too.
Same
Hey,
thing
look
there.
at that. No, unless we're using it. Yeah, we're not using it again, so.
For the last one, like these two, I could probably not do it.
Yeah,
Not add
because
it.
we're not going to use it. We don't need it again.
Nice.
And now we do the assertion, or assert equals rather. And whew, this is a fun one. U times the generator point. So we don't have the generator point.
As a constant.
Nope.
I guess you can define it.
I think here we define it. So we can probably, all right, so, my initial inclination is to just copy and paste this, but that's not the right answer, I don't think. We can, for the time being, just move this here, and we'll take this, and we'll see, I think there's a way, let me see if there's refactor, extracting the function. Nice. Perfect.
And then it returns the SACP 256K 1 point as the,
So that's cool. So now we have that generator point, and so now we can just do this times generator point plus b times point dot x. And so this is gonna be a point. All right, let's see what this is. R.
X.
Oh yeah, because we didn't. This is a mistake. We need to do multiply by u. It's the inverse because we need to use the scalar multiplication. And same thing here. So the point needs to be point multiplied by v. Maybe. Oh yeah, we have to immediately borrow v, and this is just the. Oh what? And then, so we just had to update it to be mutably borrowing the u and v variable because that's what our function used when we were doing like the bit shifting and stuff because it's the coefficient. And then it's the, what is it? It's the x value?
Yeah, I don't know where this x is coming from.
No, because it's a point, so there's an x there. So it's x. Oops.
Like px? No, not px.
No. So u times g plus v times point gives us a point. And then that point has an x value. Which, if we unwrap it and get the number...
Oh, I see.
That should be... oh, and it doesn't like it because we... didn't declare that u and v would be mutated. So that it was, here, let me just show you. So it was complaining here that you cannot borrow u as mutable because it's not declared as mutable. So we have to go up here and declare that this is going to be a mutable variable, meaning it possibly changed. And then because we used, oh yeah, we used r, so we want to borrow r here. And now everything works. Right? Because if we weren't borrowing r here, it was being moved and it was being moved and consumed. So we want to use just the reference to R, and now we can use R down below. I wonder if is this going to work the first time? Hey, no, it failed. We got two different numbers here. Interesting. Where did we screw up? Did we copy pasta all the numbers correctly?
Checking the beginnings and the ends. Yeah, they're looking good. Yeah, all the hex numbers are integral. They have integrity.
Yeah.
Interestingly, like you didn't get any errors, like that the point wasn't on the curve, that the point wasn't part of the equation.
They're just not equal to each other.
They're just not equal, yeah.
Man, makes me question everything. Well, this gives us something to figure out next time.
Yeah. Yeah, what's intriguing is that we got to the results on both sides. We got to an actual result.
Right.
Not an error.
I wonder what let me just humor myself real quick and see if cloning these does anything different. I don't think it will. But let's just find out. No, yeah, it's the same.
Same thing.
Same thing. Okay, so we can just undo all that. I wonder if this generator point is bad. Let's check. Let's just double check that. Well, let's run these other tests, I guess. So that passed. Generator point. That passed.
Try just mess up with one of the numbers just to see if you get an error. You know, just change. Yeah, whatever. For whatever. Yeah.
It completely changed the output of the first one.
But it got to two numbers in the result.
Yeah.
So that's not reassuring.
No.
Next week?
Yeah, I think next week. We overcame our technical challenges. I'm going to be streaming from this laptop and hope that my other laptop survives a little bit longer.
It shall. It will.
Right.
One final mission.
Yeah. Well, Pleb man, thanks for hanging out again. Do you have any parting words for the captive audience?
No, yeah, just keep at it.
Stay humble and stack sats, y'all.
That's it.